using technology that's a little more powerful than what our calculator is capable of. So how do we know if we're given sample data? How do we know if the normal curve works or not, right? Like if we want to use the normal distribution, we want to make sure that the distribution is bell-shaped. So there are two things, this assessing normality, there are two things you should look at to determine whether the normal curve will apply. So suppose we are given a list of data values. We can find the average and standard deviation for those data values, and we know the average, for our sample, the average should give us a good idea of the true population average, right? That's what 6.4 told us, that the sample means target the true population mean. And the standard deviation, well, it's close if our sample size is large. But it's not equal to the true population standard deviation, but it'll be close. And when I say close, I mean close to the true population value. I just didn't leave myself a ton of room to write that. If we then make a scatter plot using the original data values as the x, and then not the z-scores, we'll say, I talk about this in the video, carefully chosen z-scores, as the y, and just, yeah. Then the data is said to be normally distributed if the scatter plot is approximately linear. And I talk about how to get those z-scores. What they'll do is they'll take your x values, put them on the x-axis, and they basically try to divide it up into twice as many pieces. So if I have one data value, I just separate it into two pieces, the left side and the right side. And if that's the normal distribution, then that value should be right in the middle, and half of the area should be to the left and the other half should be to the right. And if you have two, they split it up into 4 pieces. Because if you have 2, then the average should be in the middle, right? So they add that, and then they almost do like,
so it's like,
yeah. Right. So the thing is, though, they're always going to divide it into twice as many parts as you have data points. 1 point, although how could it be a normal distribution with 1 point? It can't. But that's the idea behind it. If you have 2 data points, they're dividing it into 4 equal pieces. 3 data points into 6 equal pieces, and so on. And then they talk about how much area should be in each part of the graph. And then find, okay, what are the z-scores that give that area? Okay, I talk about this again in more detail in the video. So look at the graphs from the text. Would you say that the data are normally distributed based on the normal probability plot? So they give us 2 graphs. One is they just make a histogram for the data, and then this part is called the normal probability plot, where these are the x's and these are the carefully chosen z-values. And you want both things really to be good. You want the histogram to be bell-shaped, and you want the dots to be close to a line. But if your sample size is large enough, we don't want to be too picky about the histogram. We don't want to say, oh, this is not symmetric because that bar isn't tall enough, right? We might make a note of that at the beginning, but then we say, okay, what about the dots? Well, the dots are pretty close to following a linear pattern, so I'm going to let this slide. I'm going to call that bell bell-shaped and we can use the normal distribution. Whereas in the second graph, well, if I saw this histogram, I would say no way is that even close to being bell-shaped. But if all we had to look at was the normal probability plot, then some of these dots are close to a line, but there definitely seems to be a pattern that is not a linear pattern. It seems to be curved. So this one, we would say, you know what, let's just use the normal distribution on our calculator, but this one we would say no. Even if all we had to look at were these two graphs, if we weren't given the histograms, this one would be like, okay, use the normal, and this one we would say no. There's a nonlinear pattern. And then this one, so if the distribution starts out skewed, this is what the normal probability plot looks like. Where look at all these dots right here, and then they sort of start to level out. So that, even if we only have the dots to base on, that's definitely not a linear pattern. If we had both, we would also say no. Okay, so I give these steps for producing the normal probability plot on your calculator, and you can try this at home. But again, this is really, I'm focusing more, can you do this stuff with Excel? So this part I'm not going to test you on.